Datum transformations, fortunately, are handled routinely by the software and built into ArcGIS. There are very complex and exacting mathematical formulas for doing these that you really don't want to do by hand, especially given the complexity of data sets these days. Um, again, fortunately, the computer handles that for us. And one of the problems that we'll have is that every time you do a datum transformation, you're going to introduce a little bit of error into the data set. That's just part of what's going to happen. The more of the transformations that you do, you're going to accumulate more and more error. And the more times that you do map projections or change from one map projection to another, then perhaps to another, and perhaps to another, you're going to introduce spatial error to all the points that are in that data set until eventually it's going to have so much error built into it that it's really not usable anymore. So what you want to do, the best practices for datum transformation, do it once. The best practice for a map projection is do it once and then leave it alone from its original data. Don't reproject data that you already reprojected. If you need to change the projection information for a data set, go back to the original, and from the original, generate that new projection. Don't add generations of projection and projection and projection onto the same data set. You'll be just introducing more and more error, and your end products will be less and less reliable and less defensible in case you do need to defend them in court or in any other forum, as far as your technique goes. So a transition slide again, and now we start looking a little bit more detail at projected coordinate systems. So great couple of diagrams, figures from other texts. These are actually from an Esri textbook that are showing you this idea of map projection. So putting a light source somewhere around a glass surface, and then from that project the light onto another surface, paper, parchment, a wall, doesn't really matter what it is. And you're going to project that data out, and it's going to have a particular geometric form depending upon where that light source is, how far away it is from the center of the planet, and what the shape is of the surface that you're projecting onto. So we can see several different terms shown here. Let's look at the ones on the left first. So a planar projection is going to go onto a surface that's tangent at one point on the Earth's surface. Conic will be tangent at one or two lines of latitude, usually in one hemisphere or the other. And so conic is really good at zooming in on individual continents in a hemisphere. Cylindrical is going to be tangent at a line of latitude wrapped around the planet, usually the equator, but it can be anywhere that you want, any orientation that you want around the planet. And all of those are going to have different distortions that they introduce to the projected data set. Okay, so those are families of projections. And then over on the right, we've got terms that are referring to the position of the light source. If it's in the center of the planet, we call that gnomonic. If it's far away from the planet, we call that orthographic. So think of the sun as being the source of light. That would be an orthographic projection. Stereographic would be putting the light source on the opposite side of the planet's surface. So each one of those is going to give a slightly different geometry to the light that's passing through the surface of the planet. Imagine again that maybe this is an etched glass representation of the planet, and it casts shadows onto our surface upon which we're drawing the map. And so where that light source is has an impact on what the shapes are going to look like, where the surface itself, the developable surface, paper, parchment, or a wall, how that is applied to the globe also impacts those shapes. So it's a little bit more complex than you might have thought in terms of where these things are coming from and how they're being displayed then, the ultimate display of a map projection on the surface. And surface in this case is referring to, basically think of it as a piece of paper, and you'll probably be all right with that. So some examples, again, using those types of projections or families of projections. We often call these families because there are many different versions of these main types, hundreds and thousands of them that exist. And you have access to quite a few that are built into ArcGIS. Cylindrical, again, is going around tangent at the surface, usually at the equator. And that involves some amount of distortion. So if you look here in the northern hemisphere, we're looking at North America and seeing what kinds of distortion are happening if we use these different projections. So cylindrical on the left, we see some really interesting aerial distortion happening from south to north, where area is being exaggerated a lot to the north. A conic projection, tangent at the surface at a line of latitude in the northern hemisphere that passes through North America. This seems to be a better representation of what the continent looks like if you were to look at it on a globe. Okay, so this is doing a pretty good approximation of area and location and shape, better than the cylindrical one, if we're interested in those properties. And then on the far right, we see azimuthal or planar, where it's tangent at one point. In this case, it's tangent at the North Pole. And the further away you get from the North Pole, the more distortion is being introduced into area, shape, distance relationships. Okay. So what do you want to do with the map? Kind of is where we go when we start asking, what type of projection should I be using? Well, what do you want to do with it? What are the properties that you want to preserve in your map? What's more important? If you're interested in preserving compass directions, a cylindrical map is really good at that. It's really good for navigation. It preserves the shape and the outlines of coastal features pretty well and compass directions pretty well. But it's distorting area immensely. Okay, so that's great for navigation, but not so great for showing aerial relationships. The conic is doing a better job of that. The azimuthal, again, good for projection or good for directions away from the North Pole. A little bit better at measuring distances away from the North Pole. So, when you start getting more familiar with projection types, you'll start getting more into understanding and researching, well, what are these projections actually designed to be used for? Which one's more appropriate for what I want to do if I have a choice? Cylindrical, again, a little bit more detail on this as a family and using several different versions of it. And here on the left, we can see cylindrical being drawn tangent to the equator, or you can have it drawn tangent to a line of longitude transverse. So a universal transverse Mercator map is being drawn as if the paper was draped from the North Pole to the South Pole and around that way. Okay, so that's what transverse is meaning. It's switching the orientation of the surface that you're drawing your map upon. So we have a typical Mercator projection, transverse Mercator projection, cylindrical equal area projection, equirectangular. There's a lot of different variations of these, and each one has slight advantages for different purposes, depending on what you want to do with the map. And the way that you would discover what those advantages are is to look up each individual projection in an authoritative source and look at its properties and decide for yourself, well, which of these, of the choices that I have, which one is going to best fit what I want out of my map projection? Does it focus in and have less distortion in the area that I'm most interested in? So a Mercator projection, the strict Mercator, which is focused on the equator, where it's tangent, is really good at focusing on the equatorial zone. And it does a pretty good job of preserving map properties in the equatorial zone. Once you get out of that, north and south, we see a lot more distortion occurring in the landmass area, especially where Greenland is 3 times the size it should be, and Antarctica is immensely large compared to what it should be on a globe. Okay, there's a lot of distortion that happens there, but in the equator, it's really good. Transverse Mercator, since it's going to be tangent at one line of longitude, one meridian on the Earth's surface, it's really good at focusing in on any particular area around that line of longitude. So it might be good at looking at what we call a zone, and we split up the world into, I believe, 60 zones in UTM. And here in Idaho, we're zone 11, zone 12, zone 13. And so one of those zones might do a very good job of showing us a map oriented north to south. As Idaho is oriented north to south, it might be very good at controlling distortion around that line of longitude as it passes through Idaho, so we wind up with a map with less distortion for Idaho. And so that's kind of how these things are working. You know, we pick out what the properties are of each projection, and does it fit our purpose, our ultimate purpose in making a map, the region, the area that we want to show and depict. Conic projections, again, are good at focusing in on individual continents, focusing in on regions within the northern or southern hemisphere in particular. And here's, again, 4 different examples of that: the Lambert conformal, the equidistant, Albers equal area, and polyconic. So let's take a look at a couple of those words again. Those terms and roots. So equidistant means that that particular conic projection is very good at preserving distance relationships. Okay, conformal means that it's really good at describing the shapes of the continents. Equal area, well, very good at preserving area relationships on that particular map. Okay, so the roots and the terms that appear in the projection names give you clues as to what that particular map projection was designed for, ideally. Some of them don't. Some of the map projections are just a simple name and that's it, and you have no idea what it does unless you look up its properties. Okay, polyconic, that poly means multiple. And in this case, imagine that we were to wrap a cone around the Earth's surface so that it passed through 2 lines of latitude, which makes it a secant projection. And it's going to be really good at minimizing distortion along both of those lines of latitude. So it's going to be an even more accurate map than a single point of tangency. Okay, so a polyconic map, if the lines of latitude are centered properly, is very good at focusing in on a particular region or a continent and reducing the amount of distortion for all different map properties for that particular area. And azimuthal projections or planar projections are tangent with our piece of paper hitting the Earth's surface at a single point. Typically, these are done for the polar regions, so it would be a polar azimuthal projection. If it's done for any other location on the Earth's surface that's not the North or South Pole, then it's known as an oblique. So an azimuthal oblique projection. And the terms that we see out here on these 4 examples, gnomonic and stereographic, are referring to the light source location for this particular, or for those 2 different azimuthal projections. An azimuthal equidistant is one where we're tangent at a location, and it's very good at describing or controlling for distance relationships. It's better preserving the distance relationships. and then a Lambert azimuthal equal area. Again, as the name implies, it's an azimuthal planar projection, which is very good at preserving area. So when we look at, again, the names of these things, the names are giving us clues as to how the map projection is derived, where the light source is perhaps, what map property or what major map property it's really good at preserving compared to the other map properties, those kinds of things. So the name alone is something to examine. And if it doesn't give you enough information, then obviously we need to look into the metadata for the data set or look at the authoritative literature on map projections, such as the couple of books that are put out by the USGS that describe most of the major map projections used in North America in a lot of detail. And those are good handbooks to get your hands on if you're going into GIS work. Map projections being mathematical, statistical, geometrical things, we can come up with all kinds of weird projections that don't necessarily serve perhaps any practical purpose, but they just look cool and they're neat. Some of these here, we see the cube, the Bond pseudoconic, and the Buckminster-Fuller Dixmaxion. The cube just breaks the world up as if it was a cube, and if we cut that out on a piece of paper and taped it together, you would definitely have a cubical representation of the planet with some really weird distortions to some of the boundaries of the continents. The Bond pseudoconic is, well, can we make a heart-shaped world? Sure. That's easy. You just apply the right trigonometric formulas to all of the lines of longitude and point locations and apply it, and there you got it. And there's 5 or 6 variations of that particular projection that are out there in the literature. The Buckminster-Fuller Dysmaxion is actually doing a pretty good job of focusing in on each continent, but it uses a slightly different projection for each continent. It's more complex than I'm going to describe here. But if you looked into the history of that projection and its properties, it's pretty wild, but it's actually doing a pretty good job of showing the area relationships, the distance relationships, the shape relationships of the different continents by themselves in each of those weird panel locations that it exists on this particular map projection. So, and again, just like with regular map projections we use for analysis, these ones we might not use for analysis, but there are thousands of these special projections that have just weird geometric shapes that kind of look cool. And some of them are really interesting for displaying information in an unexpected way for your audience. If you want to surprise them a little bit, you might use a special projection. But I wouldn't throw a special projection out there if you're trying to convince the city council to do a particular action, or you're trying to convince Congress to do something. I wouldn't go that way. This is more artistic than it is scientific.